everybody, my name is Alberto Marquez. In this video we will discuss time-based statistics as we compute them in discrete event simulation. When we compute time-based statistics, we make use of the clock, and basically the kind of measures that we want to have is, for instance, how many entities there are in the system or how many entities there are in the queue, and similar measures to that. For that, we need to use a weighted average, and the weighted average is weighted by the amount of time for which there was a certain amount of entities. So let's consider that we have a graph here representing how the time passes in the horizontal axis, and in the vertical axis we will count how many entities there are in the system. First, we have an entity arrives, and the entity stays in the system before any other event happens, and no other event happens for 2 units of time. So for that amount of time, we have 1 unit. And then after 2 units of time, another event happens, and in this case, it's an arrival. So now we have an arrival, and for 1 unit of time, there is no other event. And now we have 2 entities in the system. And then the next event is a departure of the first entity out of the system. And now we have again 1 entity, and we have 3 units of time until the next event happens. So as you can see, we start to collect the weighted average by multiplying the amount of time times the number of entities. And in that fashion, as we go adding these, we will be able to compute the weighted average. If we keep running with the simulation, the next event is a schedule, it's an arrival. We have now 2 entities, and 1.5 units of time are considered before the next event happens. The next event is another arrival. Now we have 3 entities in the system, and the next event is scheduled 4.5 units of time from that arrival. And we keep going on with the simulation. The next event is a departure. Now we reduce the number of entities to 2. The next event is scheduled 2 units of time from that moment. And in this example, the last event is a departure. We have therefore left with 1 entity. We're going to stop the simulation, and at the end of the simulation, for 1 unit of time, we had 1 entity in the system. So now what we have to do is we need to consider the total time that we have. Everything that is represented here in the blue area adds up to 28.5, and the total horizontal axis of the length of the simulation, the summation of all these distinct times in which we have different heights of the number of entities, add up to 15. So that means that there is a weighted average that we can compute by dividing 28.5 by 15, and 28.5 by 15 yields a 1.9. That means that weighted average represents the height for which an equivalent rectangle we would get we have the same area as the area covered in blue. The height that this rectangle needs to be to cover that same area is the weighted average. So here we have the model MM1 that we computed in a previous video. Lambda is 5 and mu is 6, and we have in each one of the rows the definition of what happened with the entity. We generated the random numbers needed to define the time between arrivals and the service times, and we were able to compute the average time in the system, the average time in the queue, by means of each one of these entities containing its own data. So those are entity-based statistics. In order to compute the average entities in the system or the entities in the queue, that's a time-based statistics, we need to sort the events if it's an arrival or not. And if it's an arrival, we need to add it, and if it's a departure, we need to subtract it. And we need to do it in the same order in which the event happened, because we will need to compute how much time that happened. So let's start just by copying an instance of this simulation. What I have done is copy just the numbers, so the random numbers will not keep changing and there is consistency in the data. And I just copy this information of the arrivals and the number of the entity into another worksheet. And then I will mark this. This is not going to be just arrivals. Now this column will contain the clock, and the type of event will be marked in column C. This is event type A, and all of them are marked with A now. I come back to my original data and I copy the column, and I copy these starting times at the bottom of the column for the clock. I will not need the title, so I just delete that. And this event, I will mark them as B, but actually to identify that it's a starting of service, I will mark it as start of service. And finally, we copy the numbers for the entities. And we tag all those entities with the same tag. Finally, we identify the finishing times, and those would be my departures. I will copy them at the bottom. The event type C are departures. I tag all those events as departures, and now I copy the numbers. Very good. Now I will sort this list of events based on the clock. Then I will break the tie by entity, and if there is a tie in entity, I will sort that by the event type in such a way that now we can identify what happened in history. When we see A, it's an arrival. When we see B, it's a start of service, and C is a departure. So entity 1 came, started service, and left. Entity 2 arrived, started service, and left. Entity 3 arrived, started service, and before it could depart, we have 2 arrivals for entities 4 and 5, and only after that, entity 3 left. After entity 3 depart, then entity 4 could enter into the service, and before entity 4 could leave, our entities 6 and 7 arrived. So now we have the elements necessary to count how many entities are in the system, and also we will need to count for how long. So before anything happens, I will compute the difference in time from one event to another. We will have this future event, although in this particular case it's the same number, minus the previous event. And all these times that we see identify for how long the number of entities will be in that particular value. Now we count the arrivals. The arrivals we can identify if the event type is an arrival, then count it, otherwise do not count anything. and that identifies the arrivals. For the start of service, I can compute an if for the first position in the cell. So that event type, only one character. If that character is equal to letter B, then count it as start of service, otherwise do not count it. And that is the start of service. Finally, departures, we count in a similar fashion with the if. The event type, the first letter, if the first letter of the event type is equal to C, then we count it as a departure, otherwise we don't count it. And now we have every event in this list is either an arrival, start of service, or a departure. With that information, now we can count how many in the system. The entities in system will be, for the first entity is just the arrival, the first arrival, but for all the others will be the entities in the system that there were before plus the arrival. If the event is not an arrival, it will not add anything to the system. But if the event is an arrival, it will keep adding entities to the system. But of course, departures will reduce the number of entities in the system, so I need to subtract departures. So now my formula accounts for both arrivals and departures, and here you can see the net effect is we had one entity, and then for a while we didn't have any, and then one entity, and then we didn't have any, and then one entity, two entities, three entities, two entities, and so on. The entities in the queue will be at the beginning just the arrival. Now we have, for the other computation of entities in the queue, we have the previous entities in the queue plus the arrivals that go into the queue minus the start of service, because that takes them out of the queue. So it enters and immediately is not in the queue, so that is 0. We copy that, and now we have entities in the queue. Now we will compute dt times entities in system. Entities in system. So the number of entities in system times dt, just as we did in the graph in the first part of this video. And because the dt that we have for this event is 0, when we compute the number of entities time being 1, that doesn't count anything for the entity in the system, but we count it afterwards. We do the same operation for counting the dt times entities in queue. And we have entities in queue times dt. And you see these entities did not have to wait in queue, and the way that we use the computations, even though they enter the queue, they are not accounted for any impact because the DT was 0 or the number of entities was 0, etc. So only when we have entities we add them up. So what we did in the first part of this video is we added all these and the summation of dt times the number of entities in the system or the number of entities in the queue is now on the screen. And the last thing we did was divide by the end of the clock. So the end of the clock in this example is the last moment of the number that we have under that column, which in this example is, so we find the end of the column and that value is 209.65. So now we can divide the total dt times entities in system, divide by the total time, and my best estimate of the number of entities in the system is 5.53. A similar result I can compute by dividing 980 over 209.65, and the answer is 4.67. So those would be my best estimates of L and LQ as the number of entities in the system and the number of entities in the queue. So in summary, when we do time-based statistics, what we need to take into consideration is a weighted average of how long those or that number of entities happen. And the computer keeps the summation of all these numbers at all times. In other words, the way that a simulation program does it is it keeps track of the multiplication of those numbers at every time. So at any time, if they are needed, they can be used. So as the simulation goes scrolling, it keeps adding those numbers. Very good. This is the concept of time-based statistics. I hope it is clear. Thank you very much.